Welcome back to Arts Learning. In this video, we'll be going over parallel circuits, right? It's a direct continuation of last video where we went over series circuits. Okay. So what's the difference between a parallel circuit and a series circuit? This might be a bit hard to understand, right? So I'll just draw it in a more simpler way. So you go like that, you go like that, you go like that. Okay. So let's say that's, you have a circuit here, and then you hit, so it starts from the positive side, right? And you hit a node where you branch into three different wires, okay? And all of these wires, they might have different resistances. So they might each have a different resistance. So here what happens is you can't decide, right? You don't know where you can't say for sure that the current is going to go this way. It actually splits into all the ways, okay? And in varying amounts, but it actually splits into all of the ways. And for series circuits, what you'll notice is that you always know where the current's going, right? It's just always going to go from the positive to the negative end, just straight through, right? It just passes through these resistors. But for parallel circuits, they split into multiple pieces, okay? They can run simultaneously. All of these branches are going to have current simultaneously. They're going to all run simultaneously, okay? So over here, if I was to draw this, right? You have a circuit here, right? Another way I could draw this here, you move along this way, you hit a node. At that node, you branch out into two different paths, okay? One path has this resistor here, resistor 1, and the other path has just some blank, right? At that blank, you hit another node. And what do you do there? You also branch out into resistor 2 and resistor 3. So resistor 2, R3 and R2. Okay, and then all of them eventually meet up back here. So it actually, if you don't, these nodes, these don't, since they're empty, they don't really matter a lot, right? So this circuit is basically just this, split into three different branches. Okay, that's basically just what it is. All right. And there's different rules for parallel circuits. And you want to make sure you're paying close attention here, right? Because these get a bit confusing. For series circuits, so actually let me make a table to show the difference between parallel and series circuits, right? For series circuits and for parallel circuits. So for series circuits, R total, resistance total is just R1 plus R2 plus R3, whatever, right? For parallel circuits is a bit different because you can't just add the resistances, right? They all go in three different directions, or two or multiple, right? So how can you just add the resistors? You can't. There's a formula for it. It's 1 over the resistance total is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3, all the way like that. Okay, so if you had R1, R2, R3 here, your resistance total, 1 over your resistance total would be 1 over R1 plus 1 over R2 plus 1 over R3. Okay, and so that's really just, well, this one here is R1 plus R2, R1, so actually, yeah, R2 times R2, right, plus 1 over R3. So this over here would just give you, so it would give you, right here, you'd multiply R1 plus R2 here. Here you'd multiply R3. You get R3 R1 plus R2 R1 plus this here, which is R1 plus R2 over R1 R2 R3. Okay, and then you do 1 over this entire thing. Why is that? Because 1 over R total is equal to this business here, right? So you have to naturally flip it over. You have to inverse it to get R total. So there's no formula, because, I mean, there is a formula, but there's no given, like, straightforward formula, because that would just make a lot of things complicated. And you don't need to make it more complicated than it is, right? So then what happens is, I can simplify this to a series circuit. Because I know the total resistance of this entire business here is R total, I can just say that I can replace it with one resistor that I can label R total. This is called equivalent resistance, okay? So what happens is the circuit doesn't see whether the branches are parallel or series, right? It can't see it. So it sends the, so if this is R total, and if you have a series, I mean a parallel branch here, and the total resistance for this parallel branch is R total, the circuit doesn't see any difference here, right? Series here, the total resistance for this is R total. Either way, it's the total resistance is just R total, right? It's the same thing for both of them. So the circuit is going to send out the same current. And therefore, we can call it equivalent resistance, okay? Equivalent resistance. So you can substitute parallel branches with simple series branches, right? And we can say that this resistance total is just equivalent to this resistance, right? So that's just how this works. All right, now let's look at currents. So what do you remember for series circuits? You know that currents are same throughout, right? But for parallel circuits, that's not true. The currents here split. And I'll go deeper into that in a sec, but let's look at the voltage as well. For series circuits, voltages split, right? But for parallel circuits, voltage stays the same. Okay? So for example, if you had a parallel circuit like this, right? Then suppose you had, 30 volts, right? You would assume that, if you had a series circuit, if you had two different resistors, then each one would dissipate a certain amount, right? They both wouldn't get the full 30 volts. But in parallel circuits, the voltage splits. Okay. So this resistor gets the full 30 volts, and this one gets the full 30 volts. And that's exactly why the current also splits. The voltages stay the same, but the current has to split, okay? So we can say that this resistance is resistance total. We can calculate I total from that, right? It's equivalent resistance, same thing. But once we do that, then we have to understand that it's going to split here. And how are we going to measure each one for each branch? That's exactly what we're going to do, okay? How I'm going to show you how to do that. So let's try a problem. So parallel equivalent is always smaller, which works better when I show you as an example, okay? 12-volt battery, R1, so one branch here, is 6 ohms, and one branch is 3 ohms, okay? And what you need to do here is you need to find out the current total. So the thing is, you can't find out the current for each one of these and then you can't just call it a day, right? Because we don't know the current for each one of these. So what I mean by that is, for series circuits, the current flowing through both these resistors would have been the same, right? And we could just calculate the total resistance by adding them up, and we could calculate the total current. But that's not true here. The resistance total is your equivalent resistance, right? What's the equivalent resistance of this? So what does the circuit see? How much resistance is it encountering? It doesn't matter whether it's parallel or series. There's a certain amount, it's a set amount. So 1 over R total, right, is 1 over 3, which is 1 over R1, plus 1 over 6. So this is 2 over 6 plus 1 over 6, or 1/2, right? And with that, our 1 over R total is equal to 1/2. So if 1 over R total is equal to 1/2, right? If we invert both the sides of this equation, R total is equal to 2 ohms. Okay, and there you go. So this circuit is basically the exact same thing as this circuit. If, so 12 volts here, the total was 2 ohms, right? Look, it's the same thing. So the circuit can't really tell whether it's series or parallel, right? That's what we have to do to discern. And we can use equivalent resistance as a result of that. And there you go. Both of these are the same. So now we can use that to find out the total current, right? So the total resistance here is 2 ohms. The voltage total is 12. So I total is just your voltage total over your resistance total, which is 12 volts over 2 ohms, or 6 amperes. Okay, there you go. Now, a way you can check this, right, is by finding out, by looking at the rules for a parallel circuit. So what did I tell you for a parallel circuit? The voltage stays the same across both these branches, right? So 12 volts travels like this, 12 volts goes up, and 12 volts goes down. So 12 volts divided by 6 ohms is the current in this resistor, right? So the current for this resistor, which let's just call I2, is 12 divided by 6, which is R2, or 2 amps. So we have 2 amps of current over here. Here, same thing, 12 divided by 3. We're going to have 4 amps of current here. Okay. And here, you can actually add the I's, right? The I's are what you add here, because the current splits. So the total current, imagine a simultaneous current here, coming here, right? And that current is what splits into both these branches. So this is the current that splits. So what's the total current? You just add these branches currents. 4 amps plus 2 amps, we get 6 amps. And guess what? We did the exact same thing, but in a different way, right? So there's two ways to find out. Now, in the next example, we'll see how we can use the IRV charts for parallel circuits and what caveats those have. Okay. So a smaller resistor always carries the bigger current. And what that means is when you're given a parallel circuit, right? You're given the same voltage. So voltage is equal to I times R. If one resistance is big R and one is little r, right? Which denotes smaller or greater than value. Then if voltage is equal to big R, then the I must become littler to compensate for that large R, right? If R goes up, I must go down. So if you have a larger resistance, the current here is going to go down. But if you have a higher resistance, if you have a lower resistance, then the current has to go up to compensate for that. And I do go over the definitions of these and what they mean conceptually in my 7.2 video, so make sure to check that out. Okay. This video is more about the problem solving aspect of these. All right. So let's walk through this example. This is basically just, so I see 3 parallel branches here. So what I'm used to is drawing it like this. Okay, it has 3 parallel branches, so 6 ohms, 12 ohms, 4 ohms. And you could split it either way, okay? You don't need to write it in this order, but you can split it either way. Right? And that's what it looks like. Same thing, just I'm more accustomed to this format than this latter format. So this is what I tend to use more. So for resistances in my RIV chart, I would fill in 6, 12, and 4, right? And I can find my total resistance from that. 1 over my resistance total is equal to 1 over 6 plus 1 over 12 plus 1 over 4. Okay, so 1 over R is equal to 2 over 12 plus 1 over 12 plus 3 over 12 is equal to 6 over 12 is equal to 1/2. You can flip both of these. R is equal to 2 ohms, our total resistance. So I can write R tot. Okay, so my entire resistance column is now filled. Now to look at currents and voltage. So for which one? Let's see. We're given voltage, so let's start with that. Voltage is always the same, remember, right? For parallel circuits, always the same. So this actually takes the position current would have taken. 36 across each branch and 36 total. So then I is easy, right? I is equal to V over R from Ohm's law. So each branch will have a different current. And then your total will just be all of these added up. Or you could find it by dividing this voltage by this resistance. The total voltage by the total resistance. That's the one way to find out. Or you could divide each individual branch here and add the currents for each branch into a total current. Either way it works. So let's have some practice with parallel circuits. 2 8-ohm resistors in parallel sit across 16 volts. Find the equivalent resistance, each branch's current, and the total current. Okay. So the equivalent resistance, right, is the resistance total, basically. So it's basically the resistance total is what we could just write this as, right? Instead of having 2 parallel branches, we can just make it a series circuit with one branch of, one resistor of resistance total. The circuit can't see, right? It can only feel the force that it has to push to get through that specific resistor. Okay? It can feel how strong the resistor is and how much force it has to push. So obviously circuits can't feel it, but think of it in that way because it makes more sense in how circuits know what to give, other than seeing the parallel or series. Okay. So 1 over R total is 1 over 8 plus 1 over 8 is 2 over 8 is 1 over 4, right? And you can flip both of these. R total is 4 ohms. Okay, that's your equivalent resistance. And what about each branch's current? So first, I don't know whether I want to tackle the branch's current or the total current. Either one is fine. So I believe I'll go with the branch's current first. So we know that across both of these, there must be a split of 16 volts, right? So at the current reaches the node, it doesn't know what to do. It goes both ways, and both of them receive the same voltage. And I go over this more in theory in my 7.2 video, so make sure to check that out. Okay, so 16 here, and 16 divided by 8, 2 amps here. 16 divided by 8, 2 amps here. So each branch has 2 amps. Total current is just going to be both of these added, right? 4 amps. Or you could just use the resistance total. So voltage total is I total times R total, right? So in other words, 16 volts divided by 4 ohms, which is your equivalent resistance or total resistance. You can find the total current from that either. From that as well. Okay. There you go. Now let's see question 2. A parallel pair measures 4 ohms and carries 6 amps in total. One branch is 12 ohms. Okay, so basically 12 ohms here, right? And then mystery here. And then, so here. Okay, and now we need to find the resistance of the other branch and both the currents of both the branches. So we're not given the voltage, but we're given the total current, okay, which is 6 amps. So if I was to write this down in an IRV chart, which I believe would make it much easier, so I'm going to do that then. Actually, let me divide this better. Okay, so 3, so resistance 1, resistor 2, and total. IRV. R here is 12 ohms. This is question mark. But we know the total is 4 ohms, right? The total resistance or equivalent resistance is 4 ohms. The total current is 6 amps. Correct? We don't know the individual currents here. The voltage, we don't know that either. So what we can infer though, the voltage total, right, is the current total times resistance total, right? Ohm's law. So that's, in other words, 6 times 4, 24 volts. All right, and then, so actually I'm going to erase that and make it a bit more clean. from that, we can find this mystery resistor. Or, I mean, we know each of these is going to get 24 volts. That's what parallel circuits do, right? Each of them gets the same cut. 24 volts. So voltage is equal to I times R. 24 is equal to I times 12, right? For the I1. So I1 is just 2. I1 is just 2 amps. And then we know that these two currents must add, right? The question mark here. These two currents must add to make 6 because that's how parallel circuits work, right? Each circuit branch current adds to a total current. They split, so this must be 4 amps, which means this must be 6 ohms, right? Because 24 volts divided by 4 amps gives you 6 ohms. So that's how you find out. You're just using Ohm's law, right? Basic manipulation to get resistance. But the total here, 1 over the resistance total. So the way I found it, right? I found that by using 6 ohms. I just found it by filling everything else in the table, which is helpful because we need both branch currents and the other branch and all that, right? That's fine. But another way you could have found the total resistance if you were just finding, if you just wanted to find the resistance, right? If you just wanted to find this resistance, we could go 1 over R total. It's 1 over 12 plus 1 over R question mark. But 1 over R total we know, right? We're given that is 4. And then you could just manipulate this to find the R2 from that. So both ways, I solved it in a way I found more efficient. Okay, so we have this one. Let's skip for now. You can try it on your own. Let's try this one. 3 parallel branches, 20 ohms, 30 ohms, and 60 ohms, with no source voltage given. So we need to figure that out probably. The 20 ohm branch carries 1.5 amps. So 1.5 amps through the 20 ohm branch. Find the source voltage, every branch current, the equivalent resistance, and the total current. So basically, fill out the IRV chart, right? There's no point in doing all that without filling out the IRV chart. So we need 4 sections, 1 for R1, 1 for R2, 1 for R3, 1 for total. Then 1 for total section, yeah. IRV. So the resistance, we can fill that here. Just one is 20 ohms, the other one is 30, other one is 60. So now how do we find resistance total? Or actually, let's fill out what else we have. The current, or I, flowing through the 20 ohm resistor is 1.5 amps. Okay, so you want to figure out the resistance total, we could do that, but let's figure out voltage here first. Voltage is I times R is 1.5 times 20, or 30 volts. So each of these is going to be 30 volts, right? That's how parallel circuits work. Same voltage all the way across. Whoops, right. And then we could find out each current here. So 30 volts here. 30 volts, so I is equal to V over R. 30 volts divided by 30 ohms, that's 1 ampere. 30 volts divided by 60 ohms, so let me write the ohm symbol here all the way across actually. 30 volts divided by 60 ohms, 0.5 amperes. In total, 3 amperes, right? You add currents for parallel circuits. So the total resistance here, I or V total, is equal to I total times R total, right? So 3 amps times R total is equal to 30 volts. R total is 10 ohms. So you see how even though the parallel circuit makes it look intimidating, right? With a lot of branches, with a lot of high resistance, it really just simplifies to not that much, right? Just 10 ohms resistance. So parallel circuits just work that way. When you split the current in that way, it's kind of inefficient and it doesn't really take that much voltage to be dissipated because you're splitting it across so much, right? And as always, I took an alternative route. At the start itself, you could have just done 1 over 20 plus 1 over 30 plus 1 over 60 is equal to 1 over R total, but I believe that process to be more tedious. So I just solved this entire thing. And then R total at the end, I could get this. You could do that, but, you know, this worked out, right? I was still able to solve for it without needing to do anything else. So there you go. Next video, we'll go over mid circuits, which is the harder sections of of the first level of circuit analysis, okay? And then we're also going to go over really hard mixed circuits. So there's some mixed circuits that look like, not solvable by conventional rules, but when you really look at them close enough and you really start to manipulate them to try to draw the diagrams, split them into rectangles, you see that it really does break down into simple blocks. And we'll cover that in the next video. Thank you for watching. Make sure to give me a like and subscribe so I can continue helping others like you on your physics journey.